Okay, now we're going to look at the second part of the central limit theorem. Okay, so suppose that we take the commute time of students that go to a college. The distributions may look like these. Okay, neither distribution is normal. However, each distribution will have its own mean and own standard deviation. Now, the mean of this skewed right distribution, okay, you might expect to be somewhere around in here. Okay, maybe a little farther to the right. And over here, you can see if you were to average values, find the average here. Okay, there's more frequency over here than there is over here. So you wouldn't expect it right in the center of the average, okay, but maybe just a little bit off-centered. Okay, so maybe mu right around there. Remember, each of these distributions are for x, okay, a random variable x, which in this case is the commute time of students. Okay, that's random variable x. Okay, so now the idea is that we're going to take, just as before, take samples of size n from each distribution. If n is small, like n equals 2, you can compute x bar for each sample. Now again, if you go back to that sampling distribution video, okay, then you would see that if we started with the skewed distribution and a small sample size, what happened was we ended up with a distribution of the sample means also being skewed. Okay, it looks something like, okay, maybe something like this. Okay, where it wasn't quite as skewed as the original, but it was still fairly skewed. Okay, so not normal. Okay, this ended up not being a normal distribution. Okay, not normal. Okay, for the distribution over here, this was one, like you might do a custom one. And what happens there is when you take samples of size 2, well, you may get both values out of this side, find their average, plot them on the axes, take another sample of size 2, then both may come out of this side. One may come out of here, one may come out of here. Well, that distribution with n equals 2, okay, may look something, okay, maybe a little more uniform. Okay, so it may do something like this. Okay, but still not normal. Okay, definitely not normal. And again, it'll depend what the shape of your distribution starts out as, how normal, how unnormal it's going to be. Okay, so part 2 of the central limit theorem, what it gets into was the idea that if you took a large enough sample size from the population and did this resampling with a large enough sample size, then the sampling distribution of x bar will approximate a normal distribution. Okay, and again, if you go back and look at that video, you would see that when n was 25, we ended up getting a normal distribution or approximately normal distribution, no matter what kind of distribution we started with. Okay, so if n was 25, then this distribution here, if you took samples of size 25 out of it, what the central limit theorem, part 2 of it, is saying is that your new distribution for x bar, I'll just draw it down here, the x bar distribution would be normal. The mean would be the same place as the mean was here, it'd be the same value as the original. And the standard deviation would be sigma over the square root of n again. Okay, so the power of the central limit theorem, and really what's crucial here, is that we can start with a non-normal distribution as long as we take a large enough sample size, and this is the general rule that we use, is n is greater than or equal to 30. Now the applet that we used, it was 25 was the highest we could use. Okay, and that worked out to be approximately normal. But the general rule is sample size greater than or equal to 30. Okay, so that's what we're going to go with. So as long as you take a large enough sample size and do that repeated sampling to get the x bar distribution, then that x bar distribution is going to be approximately normal. Now that's important for us because that'll allow us to find probabilities again, because we can convert x bar into z. Okay, so if we look at the last example here, Okay, so just suppose the commute time, x, okay, so random variable x is our commute time, for students at a college have a mean of mu equals 18 minutes and a standard deviation of sigma equals 7 minutes. We want to find the probability that x is less than 20. Well, usually what you want to skip right to is say, okay, let's convert x into a z-score by doing 20 minus 18 over 7. Find that z-score in the table, and there's your probability. But the problem with that is we do not know if x is normal. Okay? So we do not know if our x distribution follows a normal curve or not. So that means we cannot do this question in part A. Okay, we can't do it because we don't know whether x has a normal distribution. Okay, and that's a problem for us. Before it wasn't a problem because it would have said x is normal distributed and then find your probability. So now, by the central limit theorem, if we were to take a sample of size 35 students, now that distribution of x bar, okay, the distribution for the SDSM, that will be normally distributed. And what that'll allow us to do is to use our z-tables. Okay, so if we take a sample of 35 students from this original distribution, that sample size is large enough for part 2 of the central limit theorem to apply. So we know that the x bar distribution is going to be normal, so we can draw that shape. We know the mean of the sample means will be the same as the original, 18. And we know the standard deviation of the sample means will be sigma, which was 7, over the square root of n, which is square root of 35, which is approximately 1.8. Now we're going to use that decimal of 1.8 to help draw the distribution and label the axes. 18 is going to go right in the center. Okay, so 18 is going to go in the center right here. And then we're going to add and subtract 1.18, 1, 2, 3 times on each side. And again, pause the video for the sake of time. I'm going to move on. But you can do that arithmetic. Put 18 in the middle, then add and subtract 1.8. And you end up, 1.18. And you end up with a distribution looks like this. It's a normal distribution, and the values are listed there. So now you want to find the probability that x bar is less than 15. Well, now the question is the same thing that we've answered before. We can turn the x bar into a z-score. Okay, so this is going to go very quickly here. I'm going to give you a minute to do that. Turn the 15, okay, I turn the x bar value of 15 into a z-score by doing z equals x bar minus mu of x bar over sigma of x bar. Okay, and when you put the sigma of x bar in there, use the exact value, 7 over square root of 35. Don't round it to 1.18. Okay, put the exact value in there. Okay, so the work we'll show for these, we'll draw the curve, put the value on the axes, and then find the probability. Okay, so again, for the sake of time, I'm going to show you the answer here, where it has the curve drawn, it has it shaded correctly, and it finds the probability. Okay, so if you need to pause the video, go ahead and do that. Okay, we end up with a probability of 0.0055. So again, once you understand the idea that we have a normal distribution here, the work is the same as before. Convert x into z, or I'm sorry, x bar into z, and then find the probability. Part D, x bar greater than 17. So to find that probability, same idea. You're going to draw a diagram and shade it. Okay, greater than, we're shading to the right. Turn x bar into a z-score. And again, if you need to pause the video, go ahead. I'm going to show you the answer though. On this one, you have to do 1 minus. So when you look up the z-score of negative 0.85, that's the area to the left of negative 0.85. You want the area to the right. So this area was 0.1977. you do 1 minus that to find the area to the right, which is 0.8023. So this area here, 0.8023. Moving on to part E, find the probability the mean commute time is between 15 and 20 minutes. So it'll be between 15 and 20 minutes. Now you're looking at x bar being between 15 and 20. So that's how you write that mathematically. So there you convert both into z-scores. You already did 15 as a z-score of negative 2.54. Convert 20 into a z-score. Okay, so when you do that, the z-scores that you get, and again, if you need to pause the video, go ahead. The z-scores you get, okay, that's showing you the work for it. Okay, you have x bar minus mu of x bar over sigma divided by the square root of n. The z-scores you get were negative 2.54 and 1.69. On the diagram, that's how you shade it. You're between those two z-scores. To find the probability, or the area between those two z-scores, you want to find the area to the left of 1.69 and subtract the area to the right of negative 2.54. Okay, and again, this goes back to stuff that we've already done. If you look up 1.69, that gives you 0.9545. So that's the area from 1.69 all the way to the left. That's 0.9545. And then if you look up negative 2.54, that's the area to the left of negative 2.54. That's the 0.0055 number. Subtract those, and it'll give you 0.9490, which is the area between those two z-scores. Okay, so those are examples of using the central limit theorem. Okay, and again, the central limit theorem, there's the two parts to it. The first part was if you start with a normal distribution, so if the original population is normal, then the sampling distribution is sample means, or the x bar distribution is also normally distributed for any sample size n. Okay, and these are the values we look at. The mean is the same as the population mean. The standard deviation of the x bar distribution is sigma over square root of n. That was the first part of the central limit theorem. Start with a normal, you end with a normal, no matter what your sample size is. The second part of the central limit theorem, okay, or part 2, that was if you took a large enough sample size, n equals 30, build the SDSM distribution. So basically taking as many samples as you can of size 30, like literally millions of them, plot them on your x bar axes, then you'll end up with a normal distribution when you're done. So even if you started with distribution that didn't start normal, it doesn't matter what your sample, what your original distribution looked like, you'll end up with a normal distribution at the end, with the mean the same as the population mean, and the standard deviation of the x bar distribution, sigma over square root of n again. Okay, so that should take care of sampling distributions and the central limit theorem. Okay, so make sure you practice some of those, and you should be good.